Hey kids, it's Matt here. Starting out on one of our latter topics here in solutions. This is called colligative properties. Now, colligative properties, I've got a nice definition for you up here that colligative properties are properties of solutions that depend not on what type of particle that's present, but just on the number of particles that are present. So we don't really care what they are, we just care how many there are. Now there are 4 colligative properties. We're only going to talk about 2 of them in this course. We talk about the other 2 in AP. The 2 we're going to talk about in this course are going to be BPE. This is a nice abbreviation for boiling point elevation. And what does this mean? Well, what we're going to say then is the boiling point of a solution is always going to be higher than the boiling point of the pure solvent. So the boiling point will increase indeed, always. When you make a solution, it's going to boil higher than the pure solvent would. We'll talk about them when we go into that. The other one is the exact opposite, FPD, and that's freezing point. And in this case, it's not going up, but instead quite the opposite. It's going down, a freezing point depression. Sorry, I'm missing an S in there. Freezing points go down. This is very common. This is why up north, where the roads get slick, it gets icy. What do they put on the roads? They don't just put sand on the roads. They put chemicals on the road, salt. And they want the salt that's going to break into the most particles because that's going to make the temperature lower and harder to freeze. It's not really that it's melting the ice as much as it's making the freezing point lower than it normally should be. We also see this. We put rock salt on ice when we're making ice cream by hand because that makes the ice freeze a little bit colder, and that's going to make the ice cream set up a little bit quicker. Those are the 2 we're going to talk about in here. And the 2 we're not going to talk about in here are osmotic pressure. That osmotic pressure gets lowered. And the other one, VPL, is vapor pressure lowering. And once again, we don't talk about those at this class. We'll talk about those in AP or second year. If you're open to the discussion later, really need to know something, send me an email. I'll be happy to talk with you about that. Let's talk about the 2 that do come into play. I've got these 2, and I'm going to do a couple of examples here, and then do another video where I've got a bunch more examples. So this boiling point elevation, this is what I just said. I've got it right here, that the boiling point to the solution is always going to be greater than the boiling point to my solvent. So we're going to look at this in forms of this very simple formula. Delta T, let me just write out the formula real quick so it's simple to see. We're going to go with delta T, and in this case, TB, a change in boiling temperature, is equal to KB, we're going to define him in a minute, M and I. That's the formula we're going to use for this. And that delta T is the temperature increase of the solution. What are the other players? KB is called the molal boiling point elevation constant. The KB for water is 0.51. I started to write it here, and I also have it down here. That's just a constant, and it's given. That will change for every solvent that we ever use. So we just have to look that value up. It will be provided in the problem. Has to be given to us. What that basically is how easily that boiling point is adjusted or changed by the addition of a solute. Okay, so we have that. We also have M. This is our lowercase italicized m that's going to be for molality. This is why we learned molality when we did concentration. Molality is moles per kilogram of solvent, remember. So there's your definition on molality. Moles of solute per kilograms of solvent. Keep those 2 things separate, the solute over the solvent. And I has a real fancy name. It's called the Van 't Hoff factor. And Van 't Hoff is this guy who studied, well, what happens when I throw things into solution? How many particles do they break up into? So what we find out is This I, we're going to talk about a little bit further down, is the number of ionic particles. And then I already made note, the KB is right here. Check out the units on this. Degrees Celsius per molal. Or another way you may see that is kilograms degrees Celsius per mole. That's the same thing as per molal, because really if we had our units, we would have degrees Celsius per moles per kilogram. So if I take this, throw it up, and invert it, it would be kilograms degrees Celsius per mole. That's how we get those units. Basically, it's a constant, makes the units work out right. Now at the end, we're going to want to get the boiling point to the solution. So the boiling point to the solution is going to be the boiling point of our pure solvent plus delta T, the thing we just calculated. Now in our case, we're probably going to be using water a whole lot here. So when we're using water, we just have to know the boiling point is 100 degrees. And then anything we calculate will be added on to that 100 degrees. It's always going to increase it, make it go a little bit larger. All right, that's the explanation on boiling point. I'm going to go through the explanation on freezing point now, and then we're going to do a couple of examples in this. So stick with me on the explanation. I'm going to go a little quicker on freezing point because, well, it's very similar to boiling point, just what we do with it at the end. So now, freezing point depression. The boiling point was always going to be greater than, because we add to it. The freezing point is always going to be less than of the pure solvent. So in our case, if we're using water, freezing point to water is 0. When we throw a solute into it to make a solution, that solution is always going to freeze at a negative temperature. It'll be 0 minus whatever our delta T is. That'll give us a negative freezing point. Okay, delta T is calculated the same way, just be careful. We've got delta T, KF, MI. Now we just have to watch out. That KF is going to be a different value than the KB. It's going to be a lot harder, or it's going to have a lot more of an effect on the freezing point than it will on the boiling point. So the freezing point depression of water is almost 2 degrees per molal. So it has a big effect by adding some solute to the solution, really brings that freezing point temperature down. So we pretty much have covered our delta T's here. That our boiling point scenario, right up here is boiling point. Then we come down here and we go right there is freezing point. Freezing point a little bit quicker, a little bit shorter, because it's the same process. We've already kind of defined those things out. Just make sure we're using molality, moles per kilogram. Then the last thing we want to talk about and focus on is our number of ionic particles that we've got right here that I highlighted in yellow. That number of ionic particles is how many particles these things split into. And basically, if you have something that's carbon-based, that's why I say, oh, well, it's carbon right here. If it's carbon-based, something, the poster child for this is sugar, glucose, C6H12O6. That carbon doesn't split apart. It's too covalently bonded together. It's too strong of a bond, not going to split. So that stays together. Okay, now we got to be careful with that, because we're also wanting to watch if we have an ionic solute, something like sodium chloride. Well, now sodium chloride will have a change. That's going to split into 2 different particles. And so basically what we're saying is that sodium chloride would have twice as much of an effect because it splits into 1 Na and 1 Cl. See, I'm showing you that right over here, that if we take that sodium chloride, throw it into water. This is just, you know, us making some pasta, and we got a pot of water on the stove, and we throw some salt into that pot of water. It's going to split apart. It's going to dissociate. We've talked about it dissociating before. It's going to dissociate into 1 Na and 1 Cl. It's going to split into 2 particles. Remember, colligative properties are all about the particle. So the more particles things split into, the more of an effect it's going to have on the boiling point of the solution. Okay, so if we take another ionic, CaF2, that's going to split into 3 particles. Basically, if you have an ionic, break it apart. If you have a covalent, leave it together as 1. We're going to treat this very generically on this because it can get gray if we start to look at it too confusing and we start to get too minute with it. All right, I've got 3 examples for you here. Freezing point example 1. Here you go. We've got the freezing point of an aqueous solution, so we know it's water. We got 20 grams of glucose, C6H12O6. Dissolve that in 500 grams of water. First thing we're going to do, take that 20 grams, turn it into moles. That 180 is the molar mass of glucose off the periodic table. All right, then it's going to give us 0.111 moles. Get the molality. That moles divided by 0.5 kilograms. Where'd those kilograms come from? 500 grams of water. My molality is 0.2. It's glucose, so I is 1. It's freezing point, so I'm using the KF. And I'm going to get a temperature change of 0.41. It's freezing, so I'm going to take the normal freezing point of 0, subtract 0.41, and get a freezing point of the solution of 0.41 degrees Celsius. All right, for the sake of time, I'm going to skip over example 2. That's just another freezing point example. And I'm going to go to example 3. Example 3 is our boiling point example. And in this case, we want to know what's the boiling point, aqueous again. So we know the boiling point of water is 100 when 25 grams of CaCl2. That's pretty ionic. That's going to split into 3 particles, kids. All right, that's getting dissolved in 100 grams. So take your 25 grams of calcium chloride, molar mass, 111. How'd I get that? Added it up off the periodic table. That's going to give me 0.225 moles. Take that and divide it by 0.1 kilogram. How come? That 100 grams is 0.1 kilogram. That molality is 2.25. Plug that in. Use the KB, 0.51. That's a constant given to you in the problem, and it's going to split into 3 particles. My temperature change is 3.45, and that's going to be how much it increases from 100 degrees Celsius. So the boiling point of my pure solution is going to be 103.45. I'm Smath. This is colligative properties. I've got another video coming up where we're going to do some more examples and solve a few more of these problems. Hope this helped.